It's a huge project sponsored by Shell.
Was that one of the projects that was from the joint core? Was that financed by FINEP also?
No, FINEP is halted, I guess. We had an application through CAPS. CAPS for special cooperation between Brazil and Norway, but I missed the deadline. I tried to make a cooperation with NTNU, but maybe next time.
Whom at NTNU?
Sorry?
Whom at NTNU?
Johnson. Hi, Johnson. Mm-hmm.
No, we tried to get him together with us, but
You are with Fossum C? You are work for? Okay, but in Trondheim or Oslo? I had been to your facilities, but in Oslo. Never had been to Trondheim. Maybe next time to visit the university.
Okay, I think we just start up again. So, ladies and gentlemen, next speaker is Professor José Antonio Ponciano Gomes from the Federal University of Rio de Janeiro. And he will give a presentation on challenges for analyst environment solutions simulation, impact on corrosion assessment and mitigation strategies. So I'm looking forward to your presentation.
Thank you. Are you listening? Okay.
Press the button for 3 seconds.
On the top here?
May I use this?
1, 2, 3. No? So.
No, okay.
It's okay? Good afternoon. My name is José Antônio Ponciano Gomes. I'm from the Federal University of Rio de Janeiro. My presentation is, the name of my presentation, the title is Challenges for Anodos Environment Solutions Simulation and the Impact on Corrosion Assessment and Mitigation Strategies. It's similar, it's very similar to the presentation done by Arne. And this is the content of this presentation, a brief introduction. The definition of anodos environment of flexibles, corrosion in anodos environment, I'll focus on morphology and mechanism. A few words about materials testing, and I'll show some possibilities that we have in mind to do some specific tests to test materials candidate for using in flexibles. And finally, close comments and the conclusion. Let's say a few words about our institution. It's the Federal University of Rio de Janeiro. It's the major federal university in Brazil. It's based here in Rio. We are at the Ilha do Fundão, heading the airport. We will go through the Ilha do Fundão. And I am responsible for this laboratory into the UFRG. This is the lab core. It's a laboratory dedicated to corrosion investigation. It's into the materials and metallurgy department. We do research and development, postgraduate education, and consultants. You can see an overview of the lab, the facilities. This is the first floor of the laboratory where we prepare the materials to be tested, the cells, and different setups to do different corrosion tests. The major activities in our lab can be listed as EAC, stress corrosion cracking and hydrogen embrittlement. Flow loops and erosion corrosion systems to assess corrosion under shear stress and in the presence of solid particles. High pressure, high temperature tests using autoclaves. Applied electrochemistry. A side issue that's not corrosion, but it's very interesting for us, it's the electrochemical treatment of wastewater. It's a branch of applied electrochemistry. And microscopy and all the support necessary to analysis. Of course, the laboratory is not an isolated part of the system. We work together with microscopy using scanning and transmission electron microscopy. And we do collaboration, cooperation with other institutions like this one, CBPF. And well, the subject of this presentation are the flexible pipelines. We just started working with flexible pipeline less than 1 year ago, guided by a cooperation with IFE and SINTEF and 4Subsea. Recently, we signed a contract sponsored by Shell, and we have in the horizon at least 4 years of cooperation. So corrosion is not a new issue for us, but flexibles are a new issue. So it's a challenge for us. In Brazil, we can count on about 50% of the flexibles in operation worldwide. I guess this number is precise. And we all know that the flexibles, they are a very, very complex equipment. It's a very complex technology using different materials, including metals and polymers. For us, corrosion of metallic materials is we have been investigating this issue, this process for decades. But the conjoint use of metals and polymers in the flexibles makes a different situation in terms of corrosion. And we all know that the flexibles are strategic for oil and gas production and injection, and they are used in pipelines and flow lines. Another picture of a flexible, but to show you how is the system, containing different layers of different materials. And the first layer is a metallic layer, is a carcass, commonly using stainless steels. Polymers, number 3 is a metallic layer using carbon steel in general. It's called the pressure armor. Another intermediate polymer layer, and another carbon steel, and the external sheet, a polymer. So the annulus, what is the annulus? It's the space between the internal pressure sheet and the external sheet. It's both are polymers and contain steel wires. We can assume that in this situation, there is no corrosion involved because the steel is protected from the external environment, which is the seawater by the polymer. And okay. is protected from the internal fluid by the internal polymer layer. But we all know that it's possible liquid and gas diffusion across the polymer and get to the environment. So it makes a different condition for the steel, bringing together corrosion. And another point is the possibility of external damage to the external sheet, bringing together the possibility of seawater ingress. And seawater ingress will go together with oxygen and chloride. So it makes a different environment in terms of solution, a different electrolyte. So we have too many possibilities to get to a specific condition in terms of corrosion. There is a baseline. A baseline, it was well demonstrated, well explained by RD&I, is the condensed water, a flow of condensed water to the anomalous environment, corrosion driving to a high iron concentration, increasing pH, and reduction of the corrosion rate. This is the stable situation. The system is, we used to call it a occluded cell. And together with condensed water, you can have CO2. And CO2 will drive to different corrosion mechanisms, but basically the CO2 corrosion, but with the difference that is the high iron concentration. And at the same time, from the external sheet, you can have the ingress of seawater, H2S, static and dynamic load. So it makes much more complicated to assess the possible corrosion mechanisms in the anomalous environment. Corrosion is one of the basic time-driven degradation mechanisms of flexible wear, fatigue, and aging, polymer aging. They are not isolated. There is an interconnection between the different processes. And it's necessary to improve the knowledge available to define different possibilities and different conditions of annular environment. Corrosion morphology is probably the most important aspect to be taken into account. We used to think about corrosion as a uniform process. So there is a number associated to uniform corrosion, which is the corrosion rate. So we all know that the corrosion rate in the annular space, when condensed water and CO2 are present, goes to very low values as presented by RD&I, much lower than ordinary situations of CO2 corrosion. The question is when the corrosion morphology is different. It moves from uniform to localized. And there is a lot of factors that can drive to this morphology modification. The ingress of seawater is one of them, because with the seawater comes the chloride. And even the iron carbonate precipitation can be not homogeneous. I did not mention, but the possibility of heterogeneous conditions along the axis of the pipeline is very important due to the partial ingress of water and the existence of trapped gas or air. So it makes the situation a little bit more complicated. So what we need is to know the localized corrosion susceptibility of the material in the most precise environment. And the story do not finish with localized corrosion. There is always the possibility of cracking. It's another morphology, much more critical than localized corrosion. The reasons for cracking are several. We can think about hydrogen effecting on the material. CO2, a CO2-rich environment acid, so the corrosion will be followed by any hydrogen generation. H2S ingress in the anodes environment can drive to hydrogen embrittlement, etc. Another possibility is the chloride-induced stress corrosion cracking. It's not an issue in the case of carbon steels. It's related to stainless steels. And alkaline stress corrosion cracking and different possibilities of cracking in the environment that can affect the steel in the arm wire. So the question is to understand how you can move to critical conditions where this process can occur. There is no number to express the localized corrosion because it's not very precise. It's very hard to express in numbers the resistance, stress corrosion cracking, hydrogen embrittlement cracking of a material. So you have to face a link of very complex events that goes from polymer agents to the anomalous environment. What I did. The anomalous environment. Polymer aging is a subject to be addressed by another laboratory at UFIG than this project. Gas diffusion and water through the polymer and external sheet damage. So the load conditions are very important because it can be static or dynamic. And not frequently mentioned, but it exists, the cathodic protection, any influence of a cathodic protection system. So the knowledge input is very complex to move forward with this research. I listed some of them. The pressure and temperature profiles of a flexible gas and liquid flows. I know there is a lot of models, and at least one of them was mentioned here. It's the NURSOC. The transported composition, the composition of the fluid transported can change with time, from time to time. Stress strain profile along the flexible, static and dynamic load. External pressure is due to the hydrostatic pressure. If you think about damage on the bottom, there is a hydrostatic pressure associated to this damage, and it would make possible a different situation. Materials specification are very important. I'll show an example in the next slide. The operational conditions histories are well defined and traceable. Special and repair reports. All these questions are interesting to guide a better simulation of the anomalous environment. Data fields such as the analysis of the gas vent are very important. A model, using a model, we reach the conclusion that the H2S concentration is very high. But if you collect data from field analysis of the vent gas and you do not detect H2S, there is a contradiction. It's necessary to improve the model. Mitigation technologies are very important because there is a definition of the composition of the fluid transported, etc. But we must have in mind that a lot of chemicals are commonly used in production of oil gas. One of them could be the H2S scavengers. It makes the pH different. And so it should be necessary to know it and consider or not in any simulation. The failure analysis reports are very important for feedback. Influence of cathodic protection is considered, and the possible detection of localized corrosion. This is an example of a compilation of different papers in the literature done by one of our students, a student that now he moved to Oslo. And we can see that we can identify different materials, all of them carbon steels, but with different compositions, different microstructures. And most interesting, tested using different approaches. Tested in sour environment, probably seems, it means test in an ACE solution. In sweet environment, probably CO2-rich environment. So there is a lot of possibilities in terms of the material, despite we define it as a carbon steel. The effect of hydrogen in different steels will depend on all of this property, as you know.
You have 3 minutes left.
Okay. In this case, we can see how complicated the simulation of seawater, seawater containing a mixture of nitrogen and H2S. pH of seawater is 8 and goes to 7.5. In terms of corrosion, it's not very, very critical, but the threat of localized corrosion is very important. And the same environment with CO2. So CO2 makes the pH much more acid. So we cannot define in a simple way which environment is much more aggressive for the material, depending on other aspects. So I would like to show you more results, but similar to what Ard presented, was done by our student, lessons learned from Ard, confirms the results already presented. And I'd like to conclude in what's necessary to do in terms of, in my opinion, improvement of the methodologies used to test materials candidate for use in an annular environment. We can use all the techniques we use it for corrosion. I'll not go into details and I skip these slides. These are pictures of the equipment from our laboratory for mechanical tests, static and dynamic. And a step forward, in my opinion, would be to find a way to do the same, all the tests, but on a stable, anomalous environment. So this is a challenge, because it will depend on a lot of input data, and there is a misfit between the different methodologies. The methodology used to emulate the anomalous environment has a kinetic. Arno maybe can make a comment, but you did some tests for 1 year maybe, okay? So, and the mechanical tests and corrosion tests are very, very short. So what we need is a stable environment in order to simulate the localized corrosion resistance and the environmentally assisted cracking resistance. So this is what that we should try to do for the next years. And some other aspects are very important. So the simulation of the anomalous environment done under pressure is very important, due to the, especially when we have ingress of seawater. And we know that the presence of H2S, of CO2, will be affected by the pressure and the corrosion as well.
Okay, but I think
So
we have
save
to...
some time for questions if you have any.
Yeah. We can take one or two questions now, and then I think the big discussion we can take at the end of the session. So, Daniel?
Thank you, Professor Gomez, for a very interesting talk. Daniel from Sintef. You touched upon hydrogen embrittlement being a part of the failure mechanism or contributing to the failure. How did you analyze for hydrogen in your samples?
We can use different mechanical tests such as low strain rate tests, constant load, and you can control the H2S partial pressure, different gas compositions, and we do the ordinary tests.
Yeah, but how much hydrogen is in your material after the test? How do you analyze for that?
In our lab, we used to control the aggressivity of the environment by the H2S concentration in the liquid phase.
Okay.
So it is within the range 5 to 25 ppm. Now, if you mean the amount of hydrogen into the material, okay, we can do, it's possible to do a hydrogen permeation test and to make an assessment. Or effusion tests, which means you can extract the hydrogen by increasing the temperature of the sample. But we do not do it in the lab.
Okay, thank you very much. I think we will be able to go through all of your slides after the conference. So thank you again very much. So the next speaker here is Marcelo Favar-Borges from the Federal University of Rio Grande do Sul. Oh, this is the wrong one? Yeah, okay. I'm sorry. Oh.
This one. Here. It's that one. Yes.
Okay, just go ahead.
Hello, everyone is listening. Okay. My name is Marcelo. I am from LAMEF, a physical metallurgy lab from Federal University of Rio Grande do Sul. LAMEF, I will give a short introduction about our lab. We have 6 years experience in fatigue testing and failure analysis, and 15 years performing large-scale testing. These 15 years is the major tests have been performed there is qualification of steel cables for large diameters, loads up to 1,200 tons, umbilical tests from tension, tension bending, and all the qualification tests needed for this kind of structures. Floating roses, also dynamic bending in this example, and also tension and torsion tests. Hyzers, tension and tension bending tests, VIV tests also can be conducted. And also metallurgical characterization and failure analysis like corrosion and cracking. We have nowadays 220 researchers working on these issues. So I will keep the conversation we have in the last 3 talks about flexible pipes with fluid annulus condition. Is an issue that have been studied in LAMEF since 2002. We have several projects involving this specific condition. And also other speakers have been talking about the construction of the pipe and the principal regions, the bore region, annulus region, and external environment region. We have different loads and temperature and pressure profiles along the pipe. That's the point, introducing a lot of different conditions along the pipe. So one of the biggest concerns, what's the factors that affect the flexible riser's operational performance. We have the operational stress, the assembly stresses, and the confinement ratio that are all known. We have the radial pressure gradients that will be changed along the water depth, the riser pressure gradients, the pressurization rates, the depressurization rates that will affect also the annulus condition. And these are all known conditions, but we have several unknown conditions. That's annulus pressure gradients and annulus temperature gradients, and the permeation mechanisms through the bore to the annulus, to the external regions of the pipe, and also in case of breach on external shifts, ingress of seawater from the sea. So all these conditions make this specific region, the annular region, with several unknown conditions. So we have several gaps to be fulfilled in this annulus fluid condition. That's the annulus fluid composition, the annulus fluid temperature, and the annulus fluid pressure. This can be, vary on each meter of the flexible riser, because we have the pressures and the temperatures varying along all the pipe. This will have annulus fluid condition state, annulus fluid chemical properties, corrosion mechanisms, and polymer degradation mechanisms. So all these will be factors that will affect the riser operational performance. So how to close these gaps? We have to, these reasons to solve these gaps is understand the combined effects, identify the critical operational conditions, reproduce and understand the annulus thermodynamics, provide operational conditions for material qualification, reproduce field corrosion mechanisms, determine field corrosion rates, understand and map permeation mechanisms, and predict with accurate annulus condition. This is the reasons that we need to find solutions to close these knowledge gaps. So how to close these knowledge gaps? The material testing is the first start to understand the material properties, and if you have some problems or points to be better understand on the material. Permeation small scale testing to understand how the fluids will be transported from the bore to the annulus. The corrosion tests to determine the corrosion mechanisms and the corrosion rates. Aging tests, numerical modeling, analytical calculations, and mid-scale and full-scale testing. This presentation, I will just go to the full-scale testing, but I will say that we use a lot of small and mid-scale testing to predict the conditions to be used on the full-scale testing. So here an example of small-scale testing, SEN curves in environment to get the parameters for fatigue calculation of the full-scale testing. And here mid-scale testing to determine the intensification stress factors in the end fittings. So we use all these small and mid-scale testing and a lot of other tests to determine the environments for the full-scale testing. So I will show two typical full-scale testing that have been conducted and some challenges that you need to overcome to get better results for the analyzing the performance of fatigue performance of these risers in fluid annulus condition. This test is a permeation test, full-scale permeation test. It consists in a sample mounted vertically inside an autoclave where you can put gas pressure in the bore and monitoring the condition in the annulus. So it can be done in different pressures, temperatures, and environments, and use this kind of test to determine the annulus condition for the full-scale fatigue test. This is a static test with just internal pressure and fluid annulus condition. Here you can see the setup of the test, 3 vessels with 6 meter longs and samples from 5 meter. The samples are mounted in these hacks, and the hacks are inserted in the autoclaves with hot water to simulate temperature conditions. The bore is pressurized with the CO2 or H2S in high pressures up to 500 bar, and then we keep monitoring the annulus condition up to the steady state, and after it reaches the steady state, we keep monitoring the condition, and in the end of the test, we have dissect the sample and see the corrosion rates, the corrosion mechanisms, and compare it with the conditions that we have applied as in the beginning of the test. Here are some examples of full-scale testing. This is a dynamic test, tension-to-tension test with fluid annulus, and this is a numerical modeling of the wire rupture and the local intensification factor for the tensile warmers. So we combine the results of numerical modeling and the full-scale testing to assess the fatigue. Some difficulties to run full-scale testing. This is a typical assembly of a full-scale test performed at Lameth with a 6-inch riser, loads up to 250 tons, and fluid annulus condition with seawater and CO2. We have a system developed there to prepare the seawater and inject it saturated with CO2. And then during the test, we keep recirculating some liquids to measure the O2 content, CO2 content, pH, and temperature, and iron content in the solution. So when you start to run tests with fluid annulus, we have no more access to the wires, so we need to develop techniques to monitor the wire ruptures during the test. So we have developed a lot of sensors to determine the typical signature of a wire breakage and monitor the tests to have the results compared in the end and the exact moment of each rupture have been occurred. So this is typical signature signs from angle, vibration, and acoustic emission. So it's really important to have this to understand along the test what time we have reached the ruptures. Also, tests with fluid annulus need to be run with high efficiency, because once you have stopped the test during the execution, the corrosive environment keeps acting in the wires. So the efficiency of the test is really important to have the correct combination of load and environment. So here a typical test efficiency for a full-scale test with fluid annulus. Here, during the test, the wire ruptures detected the system. And here, typical measurements of CO2, O2, pH, and dissolved iron. So there's a lot of challenge to perform tests with fluid annulus condition. This test is a low pressure, and have more challenge to perform these tests in higher pressures. After the test, we have always dissect the samples to check the failure mechanisms. We have reached, in this case, 100% failures by fatigue, and all the fatigue have been initiated on corrosion pits or corrosion lines. All these corrosion pits or corrosion lines are placed on the gaps between the anti-wear layers and the armor wires, and we have found, in this case, pitches from 200 to 300 microns. So it's very interesting results once the mechanisms proved that in this case you have major failures overcoming from localized corrosion. So thank you. Just a brief overview from the results of full-scale testing and some challenge that need to be overcome to perform this kind of tests. Thank you.
Thank you very much. Are there a couple of questions, perhaps?
Hi, Marcel. Thanks for sharing the presentation. Could you back in the slide 20 with the iron? Yeah. Could you please explain the measurements of the dissolved iron? Is it in the full-scale pipe? And
Yes.
how
all these measures are during the full-scale testing. In the beginning of the test, we have no iron content in the solution. The test was started with a new pipeline and with no corrosion on the armor wires. The solution was transferred to the pipe in deaerated condition and saturated with CO2. And besides that, we would have done this first measurement with very low contents of iron. And during the next days, the iron content starts to increase up to the saturation. And after that, it keeps saturated from all the tests.
Okay, after the test, did you measure the corrosion rates and?
Yes.
And okay.
What was the length of the test? How many months or days?
175 days, at more or less 6 months.
Yeah, so it was.
That's the time that we need to reach the rupture failure criteria.
Yeah, so the deepest attack was 300 microns, so about 0.6 millimeter per year. Mm.
Yeah.
Mm.
Okay. If not any more questions, thank you again very much. And the last speaker for the session is Svein Are Løtveit from Force Subsea. So let's see if we can find your presentation here now.
Is this the pointer? No. Is the pointer somewhere on this one? That's back and forth. For sånn rødt lys. Okay. Ladies and gentlemen, my name is Svein Are Løtveit. I'm with Force Subsea. Force Subsea is a company with these expertise areas. We are working with flexible risers and flow lines. We have some work on well intervention and drilling, and quite a bit of work on digitalization, and also some on sensor technology and on offshore wind. But today I'll only talk about flexible risers. What happened here now? There. If you go to take Force Subsea numbers, we are at the moment having 268 flexible risers, which we managed through our systems. We have performed in the range of 2,500 analyst tests. I'll come back to explaining what that is. And with respect to drilling, we have 56 wells which are monitored, but not. All these data are stored in a data reservoir. The Force Subsea mission is that we want to be a hub for managing integrity of subsea wellheads and production risers. And then we are mainly talking about flexible risers for us. And we will try to maintain production, and that means oil production and things like that, by systematic research, high-end engineering, software monitoring, machine learning, and repair solutions. We try to merge everything that we can dream of into what we do to reach this ambition. And we want, as said up there, simplifying complexity is our slogan,
And the reason for saying that is that it is, as we have been explained here today, a very complex matter, and we need somehow to make it simple to do maintenance on it. Otherwise, we will fail. We have quite a bit of ongoing research. Some of it has been mentioned already. We have, through cooperation with Shell, and Lurie talked a bit about the lifetime extension, and there is also an R&D part of this one, which is then COPPE for Subsea, IFE, and SINTEF. We are running JRP, which we call FlexShare. FlexShare is about sharing experience with flexibles. And even though we don't have equally many flexible risers operated in Norway as in Brazil, we have certainly had our share of the failures and the problems. And the petroleum safety authorities of Norway, they use a lot of effort into trying to build up some kind of database on what has been experienced. And they gave us the challenge to continue this work. So FlexShare is about sharing experience with operational flexibles. We have quite a few companies. Oh, there we were. Just find the right button. As you can see, there are quite a lot of important companies sharing their experience through this system. And we will then act as a secretary. We have a project here in Brazil, which is together with Inociano. That's sorry, yeah. Yes. This one, which is called FlexLiner Life. That is an initiative which was to try to come up with improved lifetime prediction models for flexible pipeliners. And it is sponsored by FINEP and the Research Council of Norway and Statoil in Brazil and Norway. Then we have an ongoing research project which has been done, we've been running for nearly 3 years now, with industrial sponsors Shell, ExxonMobil, Statoil, BP, and Petrobras. And we have the Research Council of Norway through their Petromax 2 program as a supporter. And we have the research partner is IFE. And Arne has already shown some pictures and something. The nice smiling flexible is from that project. Then we have this CupaFlex project, which is a JRP. The intention is to update the TR2, API 17J TR2, which is related to degradation of PA11. The upgrade is then both to improve the models in there and also to include more materials. And as you can see, a lot of operators, the flexible pipe manufacturers, and the material suppliers are part of that one. And then finally, I'll mention this project, which was then completed a few years back. This was a project, a JRP, which was run together with MarineTech and NTNU, and where the final report of that project was an update of the design and operation handbook for flexible pipes. And that has been very well received, and it's been downloaded all over the world. It's available as a free edition on the net. So what we will try to achieve is that we will try to achieve that when we are having flexible pipes in operation, it's important to have safe operation without any incidents. We want to have regular operation without any shutdown. And we want to make sure that we could utilize the full service life with an acceptable risk. Lurie told us that on several Shell fields they have achieved to have lifetime extension. We have been involved in some of them, not all. But we also have seen quite a lot of new failure modes popping up and resulting in a service life significantly shorter than what has been the design. So in average, at least in Norway, still we have a challenge achieving the design service life for how we work, we try the best we can to build up digital solutions for what we do. We get data into a data source that Laurie just presented one way of doing it and what that might be. Then we secure the data and put them into FlexTrack. You saw one dashboard that Laurie showed here earlier on. There are apps to this system which can perform validated analysis of what's in there. And you could then come up with dashboards that could be everything from a test report to an overview of status for a big system. This, as Laurie already mentioned, the big data analytics that might include vessel motion, but very often temperature, pressure, and composition of the process fluid or what's going into the riser is important. And that is very important for being able to have control of lifetime. Then we have what we call small data analytics. That means, in fact, that we need to be able to generate the apps, and then we need to understand. So we're using academic specialists, we're making calculation model, and we're using a lot of operational experience to build up models which can help us in maintaining this system. This lower here is a different app of FlexTrack than what was shown by Laurie. And here you typically will see that you have a test. The typical trend, it's year in this axis, the typical trend is going like this, and you find that you have an outlier here. And then something needs to be done. So then you compare what you test at a certain point in time with what is the expected outcome. This is then a counter just about analyst testing. So we have intelligent apps which have built-in both evaluations and visual appearance. And everything is based on a digital platform, so it's a cloud-based. So it will be available for the owner of the riser and for us maintaining the system via the cloud. And people will then have access only to their risers. That is controlled by the database system which we are operating. So it's a cloud-based, and we can integrate it with other systems such that we can automatically extract the process data, temperature data, and that kind of thing. But what is behind FlexTrack and what's behind all this? We are using offshore experience, failure investigations, and research to try to build up what we use. As I said, we are maintaining a lot of risers at the moment. We have dissected in the range of 50 kilometers of flexible pipes. We are involved, as I mentioned here, in quite a lot of research at the moment. All the research that we're involved in is then as far as we manage on the practical side to get into a position where we could improve what we try to do. Our intention is not to be a university, it's to work with operational flexibles. My intention here was to talk about the annulus and explaining the layers and all that stuff. That's been done by 3 or 4 before, so I don't think I'll say very much about that. Corrosion in the annulus has been discussed quite extensively here. But what is important to say is that this annulus here, it is due to gas diffusion into the annulus. There is you need to vent that area, and you vent the gas on the flexible risers top side. So you vent it at the upper end. This vent gas is one of the things that we use for having control of flexibles, and we do annulus testing to measure the free volume in the annulus. And we can do also vent gas composition, and Laurie showed some examples of that. On the flow lines, then there is only gas relief valves are used. That is just popping up, so we don't have the same possibility. we are then trying to identify knowledge gaps by systematic information handling. So we try to combine as much as possible from all the sources that we have. We are doing very detailed investigation if there is something which is unexpected. And normally, the operators would like us to do that, because most operators are very concerned about something which might be new, and which is something which might be a concern also for other lines. There are a lot of challenges in this one. Just handling things related to a damage is a serious difficulty. Then installation, operation, recovery, and preservation. Very often you find that it's difficult to distinguish between what has happened as a result of the recovery or what has been the failure. It might take a long time before you get into to a position of having the possibility to do a dissection. And then very often you find that the section which has failed or has a challenge is a long section. You don't know very much about it. Where to start, and you cannot always do examination of kilometers. That might be so there are several challenges related to this. This is kind of a typical slide. It gives some issues which are a bit important to or some worthwhile noticing. This is a typical North Sea configuration of a flexible riser. The upper end is connected to a floating platform, and then you have annulus volume going all the way here when the riser is new. This is then, it is not a real case. It's a typical case, but all the pictures are from real cases. At the top end here, we are, of course, concerned about corrosion, and that's partly because we are afraid of wire fracture, but also because this is a dynamic region, so any kind of corrosion up here might give you fatigue very easily. In this region, you might have air coming in from an auto cover damage. It might be above water. You may have condensed water flowing in there, and you might have a serious situation. Then, very often, if you go along here, then we have that if there is a kind of a minor leak or a leak in this one, we have seen very often that it is related to some kind of damages near an end fitting. Typically, leak through of the liner or some kind of termination damage. So very often we have a lot of efforts on the liner, but we will not talk much about that here now. Then what we often find is that this region of the riser is more or less restricted from the flow. So if you remember, I showed the graph where I shown that the free annulus volume is often reduced with time for production risers. That is related to something accumulating down here. So we have seen that after some years of operation of very many production risers, not equally much on gas risers, this area here is restricted. So we will then very often find a situation where we only measure free volume here. Then you have an area here. It might be filled with water, it might be empty, or it might be something else. But from operational experience, we then often see that if you have monitoring of the gas vent out here, which we have on quite a few risers, but not on all, then very often that is coming up in a kind of, it's a kind of trapped gas release, which is then coming up. So we have very high flow rate for a short period of time. And then you might have water filled here. And it's fair to say that very many flexibles, I don't know the exact percentage, but it's high, suffer from an auto cover damage during its service life. And flexible pipes are designed for operation with water-filled annulus. But there are some assumptions made in that, and that's been discussed here widely today. We assume that it's a confined environment, and we then build up a reliable protective film to protect against CO2 corrosion. And when it comes to oxygen corrosion from seawater, we have a CP system which is then protecting the exposed wire surfaces. So we rely on those two systems, and generally speaking, they work, but not always. Okay. This as a typical case, we found some peculiar corrosion down here. And then we need to go and discuss with people. And very often we have been consulting with IFE the last years. And these are examples of an investigation that was done together with IFE. That was then this strange corrosion spot. And if we find, in some areas, we find compact iron carbonate film, which has few defects and which give adequate protection. But then we find an area where there is a porous film, which is not giving you the protection you need, so that you could have aggressive corrosion underneath it and around it. And there were also found some peculiar particles in the annulus. That was in an area where there was not reported any auto cover damage and things like that. And there was a lot of investigations going on related to that, and found that some of these mud minerals, they had a density more or less equal to water, so they didn't, they were more or less floating for months. So we were then saying that maybe that has come in as a result of a damage during installation, but there was no damage found. And then it was then going back and doing more inspection of this one, and then finding a micro damage somewhere here, and which was probably the result of this one. So then we had a situation where some minor defect during installation had resulted in a situation which ended up with not having a reliable protection against CO2 corrosion. So that's one example. But this kind of thing is complicated, and of course, whenever we discover something, we need to build it into our evaluation and what we do. And we need all kind of support from the full audience here in order to do this properly. And we're very, very glad to have the opportunity to be in this environment where there are this academic knowledge and so much shared information. So yeah, that's a bit more about the... This is kind of, this is the very best we can achieve. If we get anything like this, then we're very, very happy, and then we can live for years and spend still all our money on doing kind of investigations to improve ourselves. So, thank you very much.
Yeah, thank you. We have time for a couple of questions, if any. I have one myself. Is there any concepts commercialized where you have a monitoring system embedded in the annulus?
But maybe Marcelo is even better to talk about that, but there are several of the suppliers have integrated strain measurements and optical fibers into their system. Maybe you also want to say a few words about it. And they are very good in that. You can measure then the strain of the wire, and you can measure temperatures, you can measure quite a bit of things. When it comes to the actual composition of the annulus gas further down, there is not that much, and it is something that we need to learn more about. As I said, the restrictions and both the actual flow restriction of in the annulus and also the radial flow restriction. Then the gas is then going through the polymer, and then it meets interlocked pressure spiral. and then it's somehow need to pass that one. We've done some tests showing that there is very large radial resistance in this one because it's an interlock system. And then, so there are a lot of issues related to it. So it would be a nice thing to have. But there is some promising tools on where you can at least have a look at what is the content of the rice. Is it oil, water, or an empty annulus? But that is by inspection from outside. But generally speaking, if you have something, it would be very good.
Thank you. Any more questions? Okay, then thank you very much. Yes. According to the program, we will close this session by a summing up and way forward discussion. So, Rolf, have you prepared something in that sense?
I have not really prepared much, but I thought that since we have had so many presentations about flexible pipes, maybe some of the audience would like to sort of make some general comments, not specifically based on one or of the presentations, but on possible ways forward. And since this is a problem which has received quite high focus both in Norway and Brazil over the last couple of years, we think that this should be an area where it should be possible to continue and broaden the research and technical cooperation between Norway and Brazil. That is sort of my general comment around this. So if anybody else has something to supply with, then please.
Well, I think I would. Well, I can speak without the mic, I think. I think this session could rather be a flexible session than a materials technology session. So I would like to comment on that because I'm a materials technology person myself, so I would very much like to see materials technology as a part of such a conference because it's one of the enabling technologies together with ICT. So I would have kind of a feedback here is should we keep the ambitions to have the materials technology as a subject of this conference? And if I ask myself the question, I would say yes, and I can say yes, because what I've learned from the presentation before from FMC and from these presentations, I think we know pretty much about the materials and the degradation mechanisms. What I think is one of the major challenges is to make these smart monitoring systems out there being reliable and give the relevant input back to a kind of a digitalized environment. So I would very much like to see as you say to bring the ICT and material technology together in look ahead for the smart monitoring solutions in the future. I think there is still significant gaps in that area, and the solutions that are out there, they are not very robust. So I think that is at least one comment from my side.
Any other general comments from the audience?
I was not here on Monday, but did they indicate that it will be a conference also next year? And will it be a call for projects? Yes. Yeah, it's a hope.
We lack authorization to publish. It's a hope. It's ready, the text is ready, but it still lacks authorization.
And the first part of the question, yes, there is plans for continuing this November conference.
Yeah. Because I guess it will be a lot of interest for flexible issues also next year. It's not solved in 1 year.
It could be a
I tend to agree. There's room for discussion on the industry on how to improve the pipes being more intelligent than they are, so finding solutions. But I also think there's a room in the industry and academy to agree on how to test materials in such a confined environment. And that's why we mix materials technology with flexible pipe, because it has to be materials technologies for flexible pipes. It's a specific environment, and we have to take that into account in our testing, and it's not easy. And I feel that many people have been doing separate things, you know, and when we go to these conferences, we see a glimpse of what we have done. And if we put everybody to talk more, and yeah, it would be great to have a standard, you know, because NACE today and NORSOC doesn't answer the needs we have. Yeah.
Okay, I think we all agree that there is more work to be done here, and that we should continue to collaborate on this and take the opportunity to broaden the Brazil-Norway cooperation in this field. By this, I will close the session, and there is a closing of the conference taking place in about 25 minutes, so that means that I hope we then have time for a little longer coffee break before that, and please stay on for the closure of the conference, where we will have the Vice Minister, Norwegian Vice Minister, Statssekretær, to close the conference and be summing up. So please stay on.